So it's my pleasure to introduce Alberto. We'll talk today about partial resolutions of symplectic singularities.
They are going to be affine. Hey, so I'm Alberto indeed. Yeah, so I'm a new postdoc here. Before this, I was at UT Austin with David, and I'm excited to be here. Be excited to chat about math with anyone who wants to, so it's exciting. Please slow me down if anything I say is unclear. I'm still kind of like learning what algebra is here. So today's going to be mostly like closer to algebraic geometry. So I'm also talking in 2 weeks. That's going to be more like sheaf theory, perverse sheaves, and stuff like that. It should, in theory, just be like a two-part talk. But anyway, so my talk's going to be on symplectic singularities. I'm assuming these are new to a lot of people, so I'm going to start with a bit of motivation. So one motivation which I find very useful is to think of symplectic singularities as a generalization of Lie theory. So I'm going to try to make that precise right now. So one thing that we study a lot in Lie theory is the nilpotent cone. So here I'm going to have the Lie theory objects, and then on the right is just going to be the generalization. So the nilpotent cone is in fact an example of a conical affine symplectic singularity. So I'll put in parentheses the adjectives that you can mostly ignore. So in particular, a more precise thing to say would be that we can think of any conical affine symplectic singularity as generalizing the nilpotent cone. Symplectic singularity. So here it is. One very important feature of the nilpotent cone is that it has a Springer resolution. So it has this highly canonical resolution of singularities, which is usually denoted n tilde. And the generalization of that is what's called a symplectic resolution. And I'll also go through all this later on in precise detail. The generalization of symplectic resolution. Sometimes we don't have a symplectic resolution and we deal with a slight weakening called a Q-terminalization, but that's not the most important right now. And then in particular, not only is there the Springer resolution, there's the entire Grothendieck Springer resolution. So I want to think of the Grothendieck Springer resolution as both n and n tilde embedding into compatible deformations. So G and G tilde, where this top deformation of n tilde lies over the vector space H, the Cartan, and the bottom one lies over the Cartan mod of algebra. So that's the Grothendieck Springer resolution. And the generalization of that is going to be the universal deformation of a symplectic singularity and its symplectic resolution. One very important datum in the package is the Weyl group, which we can already see makes an appearance right here. And it turns out that there's an analogous reflection group for any symplectic singularity which appears in the same place, and that's called the Namikawa Weyl group. So this part so far is kind of like the folklore of like the package of ways to generalize Lie theory to symplectic singularities. I'm going to include a couple of things now which are more specific to what I'm going to be talking about. So we have the Springer resolution, but it turns out that we also have some canonical partial resolutions which are in bijection with conjugacy classes of parabolic subalgebras. So if curly P is a parabolic subalgebra, then n tilde P is just defined to be pairs of nilpotent elements and parabolic subalgebras in the conjugacy class, such that the nilpotent element is in the parabolic. So if we took our conjugacy class of parabolic to be Borel subalgebras, then this would give us the usual n tilde. So what I want to say is that since in Lie theory we study a lot conjugacy classes of parabolics, and they give us these partial resolutions, I want to say that the generalization on the right is just going to be rapid partial resolutions of symplectic singularities. And again, we don't really need to worry about the adjective right now. And it turns out that not only do we have the partial resolution, but we can extend this diagram to make a whole middle column. So we can put G tilde P over here. And then this actually lives over the vector space H mod the Weyl group of the Levy. So we have a new combinatorial datum of P And that's actually a canonical combinatorial datum that we can associate to a conjugacy class of parabolic subalgebras. So this Weyl group of the levy has the structure not only of a group, but of a parabolic subgroup of the Weyl group. And so the generalization on the right is going to be what I'm going to call the Namikawa Weyl group of the partial resolution. And this is defined in my thesis. And so over the course of the talk, I'm going to explain how I define this, and I'm going to explain why, on the one hand, it's a generalization of this Weyl group of the levy, but it's also a generalization of the usual Namikawa Weyl group for symplectic singularity. So we see here, like most of the characters that people study, the most important characters in Lie theory already make an appearance, and this diagram has been studied extensively. So one place that I took a lot of inspiration from is a paper called Partial Resolutions of Nilpotent Varieties. And this is a paper by Warhol and McPherson from 1983. So in this paper, they really study the deep sort of relationship between the geometric, representation theoretic, and combinatorial data that we see in all these objects. So if we call this map rho, and we call the composition here pi, then this paper has a lot of results of the following form. So this is an example. If we take the cohomology of the fibers of the partial resolution, so this is for any element of the nilpotent cone, then these are just given by taking the fibers of the Springer resolution and then taking the invariance under the value of the levy. So we see here all of these different pieces interact. So when I saw this, I noticed that this paper was from before symplectic singularities were even invented, but I was hoping that a lot of these features and these techniques could be carried over to create something like sort of parabolic induction and restriction for symplectic singularities. So in particular, at the time, sort of this top row and this bottom row had already kind of been studied and worked out extensively, so everything in these first 4 rows. But the middle row was sort of still not there. So a lot of what I'm going to explain in this talk is sort of how we create this theory of how we work all these details out for partial resolutions with general symplectic singularity. And at the end, I'm going to obtain a theorem that sort of generalizes this one. So that'll probably happen in 2 weeks. So just to give a quick roadmap of how this is going to go. So first, I'll just introduce things like with details. I'll tell you what a symplectic singularity is, the features that we need. Then after that, I'm going to talk a bit about birational geometry. And this is going to be to obtain a combinatorial description of these partial resolutions. So in Lie theory, we have a combinatorial description for conjugacy class of parabolic subalgebras or subgroups because they're in bijection with subsets of the simple roots of the algebra. So I'm going to give you a birational geometry combinatorial description. I'm going to explain why it actually sort of generalizes that one. Then once that's set up, and here's where I'm going to define this Namikawa Weyl group with a partial resolution. Once that's set up, I'm going to talk a bit about deformation theory. So that's going to be where we actually construct this diagram and prove the properties that we need. And then once that's done, we can do Springer theory on the diagram for a general symplectic singularity. And then I'll talk a bit about sort of ongoing projects that I have based on that. Okay, so that's sort of the end of the motivation. Do we have any questions about that? All right. So in that case, let me get started. So what is a symplectic singularity? So a symplectic singularity is a normal algebraic variety. I'm going to call it X with a symplectic form. So this variety might be singular though, so the symplectic form is just on the regular locus of X. So we can kind of think of this as a generalization of a symplectic manifold, though that perspective is not going to be as useful for my class. So it has a symplectic form on this one's locus. such that for any resolution, so if we have a resolution of singularities, x bar goes to x, then the pullback of the symplectic form extends to a regular 2 form, not necessarily symplectic, to a regular 2 form on x bar. Okay, so as we said, this is not a symplectic manifold in the usual sense, but what we do have now is this gives us a non-degenerate Poisson structure on the regular locus of x. So a Poisson structure is a bracket on the ring of functions. The important thing is that the symplectic form is equivalent to a non-degenerate Poisson structure. But by normality, so because x is normal, this Poisson structure extends to all of x. So even though x itself is not symplectic, it is Poisson. Away from the regular locus, it's degenerate, but it does have a Poisson structure on all of x. So usually when things have a Poisson structure, we can study its symplectic leaves, and this tends to be some infinite, potentially chaotic, symplectic, some infinite foliation. But one of the really essential features of symplectic singularities, one of the first things that was proven, was this theorem by Kleinian from 2006, which says that symplectic singularities have finite limiting symplectic leaves. So this tends to be the stratification that we study when we want to do things like reverse sheaves. And later on, I'm going to give some examples of different symplectic singularities and what their symplectic leaves are. Okay, so now I want to talk a bit about resolutions. So if we have a symplectic singularity, so the usual definition of a symplectic resolution is that it's a symplectic resolution if the 2 form on the resolution extends not just as a regular form, but as a symplectic 2 form on the entire resolution. I'm going to slightly generalize that. I'm going to say that for any partial resolution, rho from x prime to x, rho is a symplectic partial resolution. If the pullback of the symplectic form extends to a symplectic form on the smooth locus of the partial resolution. So if it was a resolution of singularities to begin with, then it's just the usual definition. So this definition, I hadn't ever seen it before personally, but it works. So it's a known theorem that being a symplectic resolution is the same as being a Kreppen resolution, which is maybe a word that's used more in algebra geometry. And it turns out that for partial resolutions, the same thing holds. So being a Kreppen resolution is the same as being a symplectic partial resolution with this definition, even though this can be helpful in some ways. The other thing I want to mention is that symplectic partial resolutions of symplectic singularities are themselves also symplectic singularities. So in particular, if we start with a symplectic singularity, and then we take a symplectic partial resolution, then we don't leave the world of symplectic singularities. So this is critical. And the last thing that I want to mention is that, so these partial resolutions, symplectic partial resolutions, they naturally form a poset, a partially related set, and they're just covering each other. And the maximal elements have a specific description. So the maximal elements are what are called Q terminalizations. So this is not at all the usual definition of a Q terminalization. The usual definition comes from birational geometry and uses a lot of algebraic geometry words. So in particular, it's that the space is Q factorial and has terminal singularities. But it turns out to be equivalent just to being maximal elements in this poset. So the maximal symplectic partial resolutions are always Q terminalizations. They always exist. So this is just how I would think about them. And so with these 3 facts, I want to say just that for the remainder of the talk, partial resolutions are always going to be symplectic. So I won't sort of get the adjective every time. So I also want to just quickly fix the notation. So for the rest of the talk, X is always going to be a conical affine symplectic singularity. So these tend to be the ones which are studied. Conical means that there's a C star action which is well behaved with respect to symplectic form and with respect to the functions. Then X prime is going to be a symplectic partial resolution. So from now on, I'll just say partial resolution. This map is going to be rho. And then Y is going to be a Q terminalization. This map is going to be pi prime, and I'll just let pi be the composition. So this is going to be the same as in the example at the beginning from the theory. Any questions about sort of structure so far?
So why does it need to be smooth, the Q terminalization?
Oh, so Q terminizations aren't smooth necessarily. So it turns out that there's a fact that so a symplectic singularity does not always have a symplectic resolution. Sometimes people just study the symplectic resolutions. It always has a Q terminalization. Symplectic resolutions are themselves always Q terminalizations, and there's also an interesting fact that if a symplectic singularity has one symplectic resolution, then all of its Q terminalizations are symplectic resolutions.
So, say the definition of symplectic resolution, that second condition, that the pullback extends.
Yeah.
Is it equivalent just to say that the singularity is canonical?
Oh, that's actually a great question. So this is something which is important. So I wanted to mention
Or
that
is it stronger?
it's stronger. So these singularities are actually extraordinarily well behaved in terms of like the types of singularities people study in algebraic geometry. So they're always Ornstein, they're always rational. So like these are very, very high on the order of like how nice singularities can be.
It follows that it's canonical, I think.
Yeah.
But you're saying that's stronger.
Yeah, there's a lot. Yeah, there's nice properties. So Ornstein gives you conical, which tends to be super useful. Yeah. Any other questions? Okay, so in that case, I want to go through a couple of examples. So the first example I already mentioned is the nilpotent cone. I'm not going to say too much more about it, but I do want to just mention a couple of things quickly. So in particular, this Kosten-Kirillov 2 form on the regular nilpotent orbit is what gives us the structure of a symplectic singularity. So that's good news. The other very good news is that symplectic leaves turn out to be the same as nilpotent orbits. So sort of all the work that there is on nilpotent orbits and their perverse sheaves and stuff often has natural generalizations to the symplectic world because of this fact. I was considering putting this in the table at the beginning, but didn't want to add too much stuff. The other very nice example is sim n of C2. So C2 has a natural standard symplectic form, and that extends to a symplectic form on the regular locus of sim n of C2. So this has actually a unique symplectic resolution given by the Hilbert scheme of endpoints on C2. And the other very interesting thing about this example is that the symplectic leaves are given by partition type. So what that means is that if you have an element of sim n of C2, that looks like some unordered set of points, so you can get a partition by looking at like how many times each point appears, and then those are the symplectic leaves. So the symplectic leaves are in particular in bijection with partitions of n, also true for the nilpotent cone of SLN, but the behavior looks very different, sort of the closure ordering looks completely different. So that's an interesting fact. The last example I want to talk about a bit more extensively, because this isn't really just an example, it's actually going to be critical for the rest of the talk, is Kleinian singularities. So let's say we have a finite subgroup of SL2C. The standard symplectic form on C2 also gives us the structure of a symplectic singularity on C2 mod gamma. Right, these subgroups are all finite. So this is an isolated singularity. It's only singularity 0, otherwise locally it just looks like C2. It turns out that these also always have a unique symplectic resolution, usually denoted C2 not gamma tilde. Since it's an isolated singularity, the only thing that's really interesting is the exceptional fiber. And the exceptional fiber is actually very interesting because it's a union of projective lines in the shape of an ADE Dinkin diagram.
Right.
So this union of P1s in the shape of a Dinkin diagram is what people sometimes call, Malaney call, the Dinkin curve. So what does it mean to be in the shape of a Dinkin diagram? It means for every node of the Dinkin diagram, there is a P1, and those P1s intersect if and only if the nodes are connected. And it actually turns out that the intersections are always transverse. So in particular, this turns out not just to be sort of a map, it turns out that this actually gives a bijection between Kleinian singularities and ADE Dinkin diagrams. So, not only is this a bijection between Kleinian singularities and ADE Dinkin diagrams, it turns out that these are actually the only dimension 2, which is the least dimension because the symplectic form, they're the only dimension 2 conical affine symplectic singularities. So these are very important. The other thing I wanted to quickly mention, just foreshadowing a bit, is that because this exceptional fiber is just given by union of P1s in the shape of the Dinkin diagram, the partial resolutions are in particular in bijection with subsets of the Dinkin diagram, which I'll denote D gamma. So this looks a lot like this. This looks a lot like the combinatorial description in the very first section of my talk, and that's not coincidence. I also just wanted to give like an even more specific.
Sorry, so this is like Mackay
Yeah,
correspondence. Okay,
Yeah.
all right, good.
So I wanted to give an even more sort of like just down-to-earth example. So if we look at C2 mod and mod 2Z, this is the Kleinian singularity corresponding to A1. And in particular, we can compute it as a GIT quotient. So this is spec of K join XY mod plus or minus 1, which is the same as spec of K join X squared Y squared XY, which is, if we're just changing variables, we'll get spec of K join ABC mod AB minus C squared, just because of the relation in the polynomial into variables. And this can be recognized as the nilpotent cone of SL2. In particular, we know what its resolution is. It's a Springer resolution. The exceptional fiber is just a single P1. Everything behaves quite nicely. So the last thing I wanted to introduce, because it's highly related to all this, is the definition of the Namikawa Weyl group. So historically, the Namikawa Weyl group really comes from deformation theory, and I'm going to explain the connection later. But I'm going to just give a concise definition first, because it's going to be important soon. So if we have X, our conical affine symplectic singularity, we can let L1 through Lk be the codimension 2 symplectic leaves. So there's finitely many, because of the theorem of collating, it's finitely many symplectic leaves in general, definitely finitely many codimension 2 ones. Then we can let S1 through Sk be transverse slices. So these are all going to be Kleinian singularities, because as I said, they're the only dimension 2 conical affine symplectic singularities. And in particular, we can let D1 half through dk half be the corresponding Dinkin diagrams. So the reason why I have a hat is because just by varying the point that we're taking the transverse slice at, we get a monodromy action of the first fundamental group of each transverse slice on each of these Dinkin diagrams by graph automorphism. And there's a formalism for taking folded Dinkin diagrams, so we can then quotient out by this action. And taking these folded Dinkin diagrams, we can actually recover not just the AD Dinkin diagrams, but all Dinkin diagrams. And now we're going to let Wi be the Weyl group, and H sub I be the Cartan of Di, and we define the Namikawa Weyl group Wx to be the direct sum over all the symplectic leaves of Wi. So this is the Namikawa Weyl group of X. This is a definition of great importance. So this is the last thing in the intersection. Any questions about all of that?
Sorry, so for this folding, you can actually get G2 and F4 also? I mean, I understand how to get the rest of them, but,
Yeah, so G2 you take D4 and you act by S3.
oh, okay, okay.
And then F4, if I remember correctly, you take E6 and then you act like this.
Okay.
It actually turns out to be F4. Yeah. Any other questions? All right, great. So then, moving on. So, talk a bit about birational geometry. So the birational geometry of X, of a conical affine symplectic singularity, is actually controlled by this vector space, the Picard group of Y, tensor with R, as before Y essential terminalization. Before going forward, explain what I mean by that, I just want to quickly mention, this is going to be relevant later on, but this is the same as the second cohomology of the regular locus of Y. And I'm going to give credit to Alberto, Mason, Brown, and Matt Wielewski for this useful fact. So how do we get this? It's some combination of the exponential short exact sequence, but then also Gaga to get from the analytic to the algebraic Picard group. So what do I mean by this vector space controls the birational geometry of X? So let's say we have a partial resolution, X prime to X of X, then we can take its ample cone, and this is naturally just going to lie inside the Picard group of X prime, which is R. But now we can find some Q terminalization Y bar that covers X prime, and we can pull back the ample cone. And now it's going to live not here, but it's going to live in the Picard group of Y bar over X. But it's actually going to turn out that any two Q terminalizations actually only differ by a codimension 2 subset. This is essentially because they have to be the same over all the codimension 2 symplectic leaves. The important fact for now is just that this turns out to be just canonically identified with the Picard group of Y over X. So the Picard groups of any two Q terminalizations are canonically identified. So what we've obtained now is for any partial resolution, just a face inside this Picard group. So to say more precisely how this combinatorial description works, I'm going to state this theorem from Namikawa from 2013. So this theorem can be very concisely stated by saying that Y is a relative Mori Dream Space over X. Instead of saying that, I'm just going to write what we actually need. So in particular, there exist finitely many hyperplanes, HI, get B subscript, HI living inside this Picard group of Y over X, which is R, such that if we have any Q terminalization, so for any Q terminalization, Yk goes to X, the ample cone of Yk over X is a chamber cut out by the HI. And finally, the union of all these chambers has a very explicit description. So it turns out that the union over all these Q terminalizations of the ample cones is something that's called a movable cone of Y over X. So it's not super important what this is. The important thing is just that we have a situation where we have a bunch of hyperplanes. They chop up this Picard group into chambers. Each of these ample cones looks like one of those chambers. You don't get all of them like that, but there's some kind of a description for what you do get. So now I'm going to state couple examples of what this actually looks like in practice. So the first example I want to look at is the subregular orbit of SL4, the nilpotent cone of SL4. So it's not because that example has particular importance, just because it's kind of evocative. So
Sorry, I'm going slower than you. So in fact 2, the union of all the ample cones is that MOV? What is the right hand side?
oh, it's a movable cone.
The movable cone?
Yeah, it's like a different thing. So it's like the set of divisors where the base locus is codimension 2 right there. But it's not super important what actually is, more just that as a description.
But then there is a bigger fan that covers the entire vector space, right?
Yeah, are you talking about the effective cone or the?
Yeah, well, in this case, it's everything because it's a birational map. So you get a fan on the whole that peak widens around.
I think that is true, but that's not the fan I'm gonna work with.
We have some bogus cones.
Yeah. Yeah. So any other questions? Okay. So if we take the subregular locus of the nilpotent cone of SL4, so anytime you have a symplectic leaf closure and you take its normalization, you get a new symplectic singularity. In this case, this is already normal, so all good. So this fan is just gonna look like this. So there's gonna be 3 symplectic resolutions. These are gonna look like P star G mod P, for P sort of an element of each of the 3 conjugacy classes of minimal parabolic, so it's highly explicit. But looking at this diagram, what we see is that there's 8 partial resolutions. So we have the 3 symplectic resolutions, in this case they kind of 3 symplectic resolutions. The point always represents just the identity, and then we have these 4 other rays represent other partial resolutions. So I actually wanted to mention this corollary, which follows from this, which is that partial resolutions of X are in bijection with faces of the fan mod Y over X. So this fan just comes from saying we have an actual fan structure by looking at the faces of each of the ample cones and then take their union. So in this case, these are the 3 ample cones, and then each of the rays or faces, we get a total of 8 partial resolutions. Another example which I want to mention is going back to sim n.
Sorry.
Yep.
So this picture is, so X is the space that we want to collect all the partial resolutions for.
Yeah.
And what is Y?
Y is a Q terminalization, so it's a
Y is the
maximal
Q
partial.
terminalization.
Yeah, so Y is always a Q terminalization. X prime is always some intermediate partial.
Then what is
resolution.
Y bar?
So the point I was making here just at the beginning is if you take a general partial resolution, you know it's covered by some Q terminalization, not necessarily a fixed one. So I just said, say it's covered by some Q terminalization Y bar, then you naturally get a face and say the Picard group of Y bar over X. But it turns out that actually the Picard groups of all the Q
So
terminations are canonically identified. Yeah.
Sorry, I'm moving too slow.
No, that's all. Questions are encouraged. Exciting. So if we take sim n of C2, interestingly, the Picard group is just one-dimensional, and the fan just looks like this. So it's just, there's a single symplectic resolution given by the Hilbert scheme of points, and then the point always represents the identity, and that's it. And this is true for any n. So this is an interesting family of symplectic singularities of greater and greater dimension, which regardless don't have any intermediate partial resolutions. Another thing we can do is instead of taking sim n of C2, we can allow ourselves to take sim n of any other Kleinian singularity. So if we allow ourselves to take sim n, for example, so this is just an example, sim n of C2 mod Z mod 3Z, this is an A2 Kleinian singularity, suddenly things start to look very chaotic. So this is going to be 3-dimensional, so we can take a 2-dimensional cross-section of this movable cone, and it's going to look like this. It's going to look like that. So there's going to be a lot more partial resolution. So if I counted them correctly, I think there's 47. But we see each of these chambers represents a symplectic resolution. There's 12. but all the other little lines and dots represent other partial resolutions. So there's quite a large number of them. And actually, if we let the number here go up, the number which we're taking the symmetric powers of, sort of each time we add more and more lines. So this thing can get increasingly crazy. So next I want to define this Namikawa Weyl group of the partial resolution. So the Namikawa Weyl group was basically defined in terms of looking at the codimension 2 symplectic leaves. So I'm going to have to look a little bit harder at those. So I'm making a new definition. So the essential cone call it S of y over x. So this lives not in the Picard group, but it lives in the vector space of curves contracted by the y-tax map. So this is the cone of curves. So the essential cone is the cone generated by all curve classes living over codimension 2 symplectic leaves. So we kind of have a sense of what these look like from before. So if we take some point xi inside some codimension 2 symplectic leaf, we recall that the preimage of xi in the Q generalization is a Dinkin curve. So it's a union of P1s in the shape of a Dinkin diagram, and it's a Dinkin curve of type di half. So the Dinkin diagram corresponding to the Kleinian singularity, given by taking a transverse slice. But it turns out that two curves living inside this bouquet of curves are in the same curve class if and only if they are permuted by the action of the fundamental group. So we kind of recover the same Dinkin diagram from before. Only if they are in the same pi1 of Li orbit. So being more tangible about what this means that generators of the essential cone that live over some symplectic leaf Li are in bijection with nodes of corresponding folded Dinkin diagram. Now if we look at the generators of the whole essential cone, then we'll get the nodes of all the Dinkin diagrams. And in particular, those are in bijection with generators, simple generators of Namikawa Weyl group. So if we take all the generators of the essential cone, then this is actually in bijection with simple generators of this Namikawa Weyl group. So given a simple generator S, I want to call the corresponding curve C sub S. And it turns out that, so there's a pairing between the Picard group and this cone of curves. So if you think that the Picard group is given by divisors, that's just the intersection pairing. But in particular, if I take the dual to this ray, or to the ray generated by C sub S, I'll get a hyperplane in the Picard group, and it turns out that it's one of the HI. And I'm just going to call it H sub S. Okay, so finally this allows us to get to the definition. So given partial resolution, so if we have a partial resolution, x prime goes to x. We talked about before how this corresponds to some face f inside the Picard group of y over x. So then the Namikawa Weyl group is the subgroup generated by all the simple generators such that f is contained in HS. So Namikawa Weyl group W sub x prime is the subgroup S such that F is contained in HS. So this kind of seems like a bit of a mouthful, but if our resolution was covered by Y, then we can just look at which curve classes are contracted, and that tells us precisely. Like, if F corresponds to some face, which is a face of the ample cone of Y, then it being contained in this hyperplane is just equivalent to it contracting the essential curve class corresponding to X. And if it's covered by a different Q terminalization, we can identify the Picard groups and do a bit of work.
I'm a little confused.
Yeah.
So F is in Picard.
Yeah, F is the
In the
corresponding
curve.
face, yeah, of the moon. Yeah.
Lives in Picard. S lives where? S is a curve.
S is a simple generator, the Namikawa Weyl group.
So that corresponds like to curve.
It corresponds to to a generator, the essential curve. It corresponds to an essential curve class. So if we take a simple generator for the Namikawa Weyl group, this corresponds to a node of one of the Dinkin diagrams, and then those Dinkin diagrams
Right.
are exactly like the curves given by this pre-image of a point that we mentioned to symplectic leaf, so you get like
Mhm.
an explicit curve class that corresponds to that.
You're mixing, line bundles and curves. I'm confused.
Oh well, so they're both going on. So the essential cone lives inside the cone of curves,
Yes.
and everything else so far they've introduced those inside the cone of divisors.
The dual vector space.
Yeah, exactly. Yeah. So there's the parity. So if you have one of these essential curves, it
So
turns out.
what is the HS? This is perpendicular to S.
Yeah, exactly. Yeah. It's yeah. So.
You wrote that.
Yeah.
Per person.
Yeah. Does that make sense? Yeah. This is probably the moment where like the most happens. And I'm gonna go back to these examples in a second. Hopefully that will make it better. But maybe I'll state the theorem. So this is sort of the theorem that this is the main theorem of the birational geometry section. So this definition was in my thesis. It's sort of the thing that I alluded to at the very beginning. And then this theorem. So this definition gives us a map from partial resolutions to parabolic subgroups of the Namikawa Weyl group.
Mhm.
So it turns out that this map is surjective. It's always surjective, and it's bijective if and only if there is a unique Q terminalization.
Mhm. Right.
See if your X prime is one of these Q terminalizations.
So
No.
X is just a general partial resolution.
Say
Right.
X prime is Y.
Well.
Say it's a Q
Okay, yeah.
terminalization.
Mhm.
So then the cone is maximal dimensional.
Yes.
And
So the Namikawa Weyl
W
group
is trivial.
Yes. So the part of this theorem. So exactly. So if we have a Q terminalization, it's always going to have trivial Namikawa Weyl group. So actually, maybe it's good to just go through these examples. So in this case, for this first example, the subregularity of SL4, the Namikawa Weyl group is Z mod 2Z. The corresponding hyperplane is this one. It has a single generator.
Mhm.
So we have three different partial resolutions with Namikawa Weyl group Z mod 2Z, and 5 different ones with trivial Namikawa Weyl group. On the other hand, in this case, the Namikawa Weyl group is also Z mod 2Z, but we have an example where there is a unique Q terminalization. So there's actually, as soon as we knew that the Namikawa Weyl group was Z mod 2Z, and that there's a single Q terminalization,
Right.
there's actually no way there could have been other partial resolutions. So
Right.
we have the identity, which corresponds to the Namikawa Weyl group Z mod 2Z, and we have the unique resolution, which has full trivial Namikawa Weyl group. This example is a lot more chaotic, right? So here the Namikawa Weyl group is Z mod 2Z, direct sum S3. So we have that this is the hyperplane corresponding to the generator Z mod 2Z. These two on the side are the ones corresponding to the simple generators of S3. And if I counted correctly, I think there were 31 partial resolutions with trivial Namikawa Weyl group, and then like 5 with Namikawa Weyl group the two simple generators of S3, and everything else had a single one. So the important thing to note is that this Namikawa Weyl group with a partial resolution has the structure not just of a group, but it has the structure of a parabolic subgroup of the Namikawa Weyl group. So it has a bit more data, similarly to the way that the Weyl group with the Levy had more data. So in this case, if you started with, if you just going back to the very beginning, if you took the nilpotent cone and you took some n-over p, then this would just go to the Weyl group with the Levy. So it is sort of a strict generalization of that map. The other thing I want to mention is that this sort of, the original Namikawa Weyl group comes from deformation theory, and next I'm going to sort of explain why this definition also makes sense from a deformation theory point of view. Any questions before we do that? All right, so deformation theory. So we can take for any, if we have a Poisson scheme, or really you could also do for a Poisson complex analytic space, that's not super important. You can take its deformation functor from Martinian rings with residue field C to sets. So this is defined sort of the usual way. So we send A to the set of schemes XA over spec A, which are flat and Poisson over spec A, along with an identification between the special fiber of XA with the thing we started with, so we're taking deformation with. This is up to isomorphism. So this is the usual animal. So these functors were studied like very, very extensively by Namikawa over the series of a large number of papers and large number of years. So I'm going to summarize some of the results that he has by these. So Namikawa studied the Poisson deformations of X and of its two generalizations of Y. And what he found is, first of all, that PDX and PDY are always pro-representable and smooth, but sometimes people say unobstructed. If you combine these, what it actually tells you is that the ring which represents this has to just be the ring of a formal neighborhood of 0 in the tangent space. And in particular, you actually get a universal deformation over the formal neighborhood of 0 in the tangent space of the functor. And then that tells you basically everything about these functors. The second thing he found is that the tangent space of the Poisson deformations of Y is isomorphic to the second cohomology of the regular locus of Y. So this is, except that we base change to C, the same vector space that controlled birational geometry also appears here, controlling deformation theory. We also construct an action of a Namikawa Weyl group on the space. Then there's a push forward functor from the Poisson deformations of Y to the Poisson deformations of X. This is sort of highly unusual. Usually you don't see, you can't really push, there's no reason in general why you should be able to push forward deformations. That's not a standard functoriality.
Yeah. So X and Y here could be complete, could be not complete, or could be, probe or non-probe, compact, non-compact, right? X and Y.
So yeah, so it's interesting because they're not compact, so they're affine. And that's actually why Poisson deformations turned out to be the right thing. So in the past, people.
I mean, X could be compact, right?
No, it's conical. It's conical affine, so it's actually never compact.
It was just a symplectic, right?
So throughout, I mean, these are.
How about the K3 surface? Is that an example?
I don't think K3 surface is conical. So it can be contracted to what the conical action does is it can be contracted to a point. It's always. So I don't know if I ever went into great detail about it, but X is always a conical affine symplectic.
Was X like affine to begin with?
Yeah, it is affine. Yeah.
That was part of the definition.
Yeah.
X was affine.
And also
affine.
conical. Yeah.
So X is local. Right? Okay, affine.
Yeah, it's true. Yeah. Yeah, exactly. Yeah. So I mean, just as a historical note, like people used to study the deformations, just the flat deformations of like projective symplectic singularities, because these weren't well behaved. The flat deformations weren't well behaved. But it turns out that if you study the Poisson deformations, there's some regularity along the strata which is imposed, and it turns out to be well behaved again. So that's sort of why we're studying these. That's why Namikawa was studying these. So the last point is that
You're saying X is contractible.
X is totally
Yeah.
contractible.
So,
Yeah.
like H2 of X reg, that's just trivial.
Yeah, H2 of X is always trivial, but Y is, or yes. Yeah. So yeah, it's I mean, it's a cone. Yeah, exactly. So the last thing is that there exists a universal deformation, and this is also, so Losa did some work here sort of getting the correct universal property, but there exist universal deformations. So the correct adjective is conical, exist universal conical deformations. So I'll just draw the diagram. So we have y going to x. This embeds into its universal deformation. X also embeds into its universal deformation. And this lives over the space, which is just the tangent space. So the second homology of the regular locus of y. But then this turns out to be just the base of y mod the Namikawa Weyl group. So this Namikawa Weyl group really controls the difference between the deformations of y and the deformations of x, and this is where it came from initially. So the other thing I want to notice about this is that these deformations are actually over the entire tangent spaces, not just the formal neighborhood of 0, and that's because we can use the conical action. And actually, if we state a universal property correctly, these are still the universal deformations which behave well under the conical action. So, so the main sort of theorem in sort of the deformation theory part of my work is just sort of doing the analogous things for partial resolutions. So, first of all, for all partial resolutions x prime, PD x prime is pro-representable, and unobstructed. Second of all, the push forward of Poisson deformations actually factors through Poisson deformations of the partial resolution, so that's good news. And lastly, the analogous thing, so we have a diagram of universal conic deformations. And what I want to do is I just want to add it to the existing diagram. So everything which is already there already was done by Namikawa and was already known. And but now the diagram also has the partial resolution, and it also embeds into this universal deformation. And then there, this universal deformation actually lives over the base of the universal deformation of y, mod the Namikawa Weyl group of the partial resolution. So this is exciting for two reasons. So reason one is that we see that the Namikawa Weyl group of the partial resolution satisfies essentially the same deformation theoretic condition as the original Namikawa Weyl group. So the original Namikawa Weyl group measured the difference between deformations of y and x. The new Namikawa Weyl group for partial resolutions measures the difference between deformations of y and x prime. The second reason why this is exciting is because this actually is a diagram that we need to do what I was alluding to at the beginning, to do Springer theory for partial resolutions of symplectic singularities. So if we were working with the nilpotent cone, this is exactly the same diagram that I drew at the beginning, but without having some universal object which x prime embedded into, you can't really do Springer theory correctly. It doesn't really work. So this is going to be the diagram that allows us to do that. So that's the next section of my talk. I wanted to give a very quick explanation of why this theorem is true and then how that proof carries over. So let's start maybe with what Namikawa does. So the first thing you need to do is you need to start with Kleinian singularity. So if you have a Kleinian singularity and its resolution x prime, then taking a transverse slice to the subregular orbit of the corresponding Lie algebra, you actually obtain the universal deformation. You obtain universal deformation, so these both embed inside universal deformations, and that comes directly from the theory. And now this is where we first see H and H mod W appearing. Now the next thing we can do is, if we're starting with a symplectic singularity and its resolution, we can restrict just to a little neighborhood around each codimension, around a point in each codimension to symplectic leaf, and then to a little neighborhood of its pre-image, and we actually get a sequence of functors. So we knew before that PDX mapped to PDY, but now these restriction maps gives us a map to direct sum over all the codimension to symplectic leaves of deformations of the corresponding Kleinian singularities, and then similarly we get a map to the deformations of their resolutions. But these maps are all well behaved. They're all sort of pro-representable, unobstructed. So it's all actually determined just by looking at the bases of the universal deformation spaces. So this is dx, this is dy, and then these are hi tilde and hi tilde mod wy tilde, where those are the Carpanda-Weyl group associated to the unfolded Lincoln diagrams. But then if we look at the image of this map, it actually just turns out to be the invariance under the action of the fundamental group. So we get a map. So we get a map like this. And then this map actually turns out to be Cartesian, but the direct sum of all those Weyl groups is just a Namikawa Weyl group. So that shows the appearance of this Namikawa Weyl group over here. That's the work of Namikawa. Now to make it work for partial resolutions, should I keep going or should we just pick up?
I have to go at 5, sorry. And it's 5.
It's definitely 5, yeah. Alright, well we can pick up next.